Welcome to The Explainer. Today, we're tackling a huge question. How do you actually design a clean, green energy future for an entire continent? Let's get right into it. So, just think about this for a second. How would you even begin to design a power grid for a whole continent, especially one that's supposed to run almost entirely on renewables? I mean, this isn't just a fun little puzzle. It's a massive, real-world challenge that engineers and planners are wrestling with right now. And to really get a handle on this challenge, you've got to understand that the power grid we've known for 100 years, well, it's being totally rewritten from the ground up. I mean, think about all the new pieces. You've got power from wind and solar. That's, well, it's as unpredictable as the weather, right? It's not like a steady old-school power plant. At the same time, we're adding all these huge new demands, millions of electric cars plugging in, homes switching to electric heat pumps. And then you've got batteries, which are wild because they can both suck power from the grid and push it back in. This whole thing isn't a simple, predictable system anymore. It's this dynamic, incredibly complex network. And here's the problem. The software of the tools we use to plan and manage that old grid, they just weren't built for this new world. It's like trying to navigate rush hour traffic with a paper map from the 1980s. It just doesn't work. Yeah, the old tools were basically like a snapshot camera. They were designed to analyze one single, stable moment in time. But our new grid, it's a full-length movie. It needs to be optimized across an entire year, taking into account this crazy dance of renewables and storage literally every single hour. The old tools just, they can't handle that kind of complexity. So obviously we needed a new tool. And it's called PyPSA. That stands for Python for Power System Analysis. And honestly, the best way to think about it is like a super powerful modern GPS for our new energy grid. So what is it really? Well, at its heart, PSA is a free, open-source software toolbox. It's built to simulate and find the best possible setup for modern power systems, looking at hours to years. And that open source part is a really big deal. It means anyone, anywhere in the world, can use it, check its work, and even build on top of it. It was designed from scratch to handle all this new complexity, the variable renewables, the energy storage, and even linking the grid to things like heating and transportation. And the creators of PyPSA themselves, they just put it perfectly. Their argument is, look, when we're talking about making these enormous, multi-billion-dollar investment decisions about our energy future, the tools we use have to be transparent. They have to be verifiable by everybody, not locked away in some corporate black box. It's all about accountability. So how does this GPS actually find the best route? Let's peek under the hood and see how it takes this mind-boggling complexity and turns it into a clear, lowest-cost plan. Okay, so PyPSA starts by just gobbling up a massive amount of data. It looks at years of weather data to figure out wind speeds and how much the sun will shine. It uses forecasts for how much electricity we're going to need hour by hour for a whole year. It knows the cost of everything, every wind turbine, every solar panel, every battery. And critically, it knows the physical limits of the grid we already have, like how much juice each power line can actually carry without frying. Now, to understand how it pieces all that together, you got to know about this core idea called a bus. And no, it's not a vehicle. In grid speak, a bus is basically a meeting point. Think of it like a major intersection on the electrical highway where everything connects, the power plants, the transmission lines, and the homes and businesses using the power. Right, so once it has all that data and it has the whole network of these buses mapped out, PyPSA's main goal is something called optimization. And that's really just a fancy word for finding the absolute best plan. It runs this gigantic calculation to find the single cheapest way to build and operate the entire grid so that it meets demand in every single bus for every single hour of the year, all while making sure, of course, that the lights stay on. So that all sounds great in theory, but what happens when you actually point this powerful tool at a real-world problem? Well, let's see what happened when it was used to create a blueprint for a green European grid. So researchers gave it a really ambitious target: design a European grid that cuts CO2 emissions by 95% compared to 1990 levels. And what it spit out is pretty fascinating. And here it is. This is the result. It's literally a blueprint for a continent powered by clean energy. The model creates this map, see? Each one of those circles is a major energy hub, or bus. The size of the circle tells you how much power capacity is needed there, and the colorful slices show you the perfect mix of wind, solar, and storage for that exact spot. Now if we zoom out and look at the big picture, the overall energy mix for the whole continent, You see it relies heavily on onshore and offshore wind, plus a lot of solar. But, and this is so important, it's all balanced by two key types of energy storage: batteries and hydrogen. And this is what's so cool. The model basically discovers this brilliant geographic strategy all on its own. Down in southern Europe, where there's tons of sun, it pairs solar panels with short-term batteries to keep the power on overnight. Makes sense. But up in northern Europe, where you have these incredible wind resources, it pairs wind turbines with long-term hydrogen storage. And why is that? Because sometimes the wind doesn't blow for days at a time, and you need a way to store huge amounts of energy for much longer than batteries can handle. And here is the absolute kicker. The model shows that the average cost of electricity in this new green system would be around 82 euros per megawatt hour. It could even drop to 65 if the grid is expanded. You know what that is? That's competitive with today's prices. This is the crucial takeaway. It shows that building a near-zero carbon energy system isn't just some technical fantasy. It's actually economically viable. This is a real plan for decoupling our prosperity from pollution. And that kind of leaves us with this final, really powerful thought. Tools like PyPSA, these incredibly powerful, transparent, open-source models, they're now available to everyone. They're basically democratizing the very process of designing our sustainable world. So the question isn't really, can we figure this out anymore? The real question is, now that we have these tools, what kind of future are we going to choose to build?